we are very happy to listen to Struyve from KU Leuven. It's a great pleasure to listen to you. Thanks a lot.
Okay, thank you, and thank you for having me here. So this is a talk about Bohmian quantum gravity. So I was very happy with the talks before me because they gave a lot of introductory material that I can reuse here. So as you all know, classical gravity described by Einstein's theory for general relativity can't be the right thing, right? Because matter is quantum, so something has to change, right? Either we have to incorporate quantum matter in the classical gravity, or maybe you have to find some quantum theory for gravity. Okay? And as Klaus said, well, there's a lot of ideas on the table of how to proceed devising such a theory. Okay? But the most conservative approach is just to quantize classical general relativity. So you just apply the usual quantization methods that were so useful, so successful in deriving theories like QED and QCD, and you just apply them to general relativity and see what comes out. Okay. And similarly, loop quantum gravity, it's also in this ballpark. So canonically quantizing general relativity gives you the Wheeler-Dewitt equation, but using a different representation, and you get to loop quantum gravity. So how do these methods work? So as usually, you first go to a Hamiltonian formulation, splitting of space and time, and you describe the dynamics of your things evolving in time according to some spatial slicing. And for gravity, what you do is you start with writing the metric, g mu nu, in terms of these other variables. So n is called a lapse function, and I shift function, and then you have this hij, this is a spatial metric. Okay. And then this Hamiltonian form of Einstein's theory, I've given the equations here. So what's important is you see an equation for this three-dimensional metric, okay, and its conjugate momentum. Also some equations for the scalar field, so I've assumed here there's a scalar field as matter. There's no equation for n or ni, so these are completely free. So these are gauge freedoms, and you have a geometrical meaning. Okay. So in short, this dynamics is kind of like telling you how a three-metric or three geometry evolves in time. If you apply the usual quantization rules to that, well, you get a wave function which depends on this three-metric and, say, a scalar field. What you also get is some Schrödinger equation, time derivative of psi is some Hamiltonian of psi, and there's some constraints. And this is this curly h there. Curly h on psi has to be 0, and hi on psi has to be 0. What this entails is that also the Hamiltonian on psi, is capital H on psi, is 0. So you conclude that, okay, my wave function shouldn't depend on time. Okay? So if you follow this recipe of canonical quantization of the classical theory, you get to an immediate problem. Okay? There seems to be no time evolution. So how can this theory account for our evolving universe? The universe is supposed to expand. How do we get this out of a wave function which is static? Okay, so this is the problem of time. But there's more conceptual problems with this theory, right? Some of them, these have been mentioned before, okay? What to do with the collapse postulate here in this theory, okay? So the wave function is supposed to collapse upon measurement. What do we do with this here in the context of quantum gravity? So we get to the measurement problem. Okay. Also, what's the nature of this wave function? Okay. Is that the only entity? Is it a real entity, or is it more of a statistical nature? Okay. So this measurement problem and ontology problem, of course, hang together. Okay. So finding solutions to these problems probably goes together. In addition, people have been worried about maybe quantum gravity will solve the problem of singularity. So in general relativity, space-time singularities, these are unavoidable. What about quantum gravity? For example, one of the selling points of loop quantum gravity is that it would solve the singularity problem. But the question is, if the wave function is the only thing there is, okay, so what does it mean to have a space-time singularity? If there's no space-time fundamentally, there's just a wave function on these three metrics and a scalar field. What do we mean by singularity? And then the question of how to account for primordial fluctuations. Okay? That has come up in a couple of talks. How do we account for the primordial fluctuations? And another worry with these fluctuations is, or that some people have raised, is in the late universe there will also be quantum fluctuations, and these rise to a problem called the Boltzmann brane problem. Now, so the way I'm going to address these issues or try to get an answer to these questions is starting from this Bohmian approach. Okay? So how does it work non-relativistically, this theory? It's a theory that was invented by De Broglie in 27, and then reinvented by Bohmian in 52. And according to this theory, on a non-relativistic level, the world is made out of point particles. Okay? Tables and chairs, they're made out of point particles. And the way they move is by first-order dynamics, where the velocities of these particles is a function of the wave function. And the wave function itself always satisfies Schrödinger's equation. So no collapse, so also no measurement problem. Okay. For example, these are, probably you've seen this before, so these are the trajectories for the double-slit experiment. And if you do the experiment, like, just one of these trajectories is realized. Also, one can argue that, like, the usual quantum statistics follows from this theory, that typically you will have the mod psi squared distribution for positions, okay? And from that, one can argue, okay, that actually for any experiment, because at the end of the day, all experiments are recorded in positional things, you get the usual quantum statistics. Okay? But what one usually says is, well, one get the usual quantum predictions, insofar these are unambiguous, okay? And like, Schrödinger's cat is going to be alive or dead, not because the wave function has a certain shape, but because the particles will be configured either in a live cat or a dead cat. Okay? So one can construct Bohmian theories for all kinds of quantum theories. Okay, so this was just non-relativistic quantum mechanics. If you have other quantum theories, you can play the Bohmian game and introduce some Bohmian dynamics. Okay? And what's crucial usually is something of the following form. So if you have a continuity equation for here, it's the mod of psi squared, so the usual position distribution. You can introduce velocities which are given by the current divided by the density. Okay, so the integral curves of the probability current, these are my Bohmian trajectories here. Okay. In other theories, you have to think of a good ontology, and then you can introduce the dynamics in this way. Okay. So some important properties that will be important later on as well. So one of it is that, well, if you look at this first order equation for the particles, you can take a time derivative and get something that has a Newtonian form. On the top right, you see the Newton's equation, but with an extra potential. Okay, so this equation comes out of the Bohmian dynamics, and you can use that to study deviations from classicality if you wish. You can, of course, do everything in terms of this first order formalism, okay, but sometimes it's handy to have the second order formalism as well. Another thing is the notion of the wave function of a subsystem. So according to the Bohmian theory, there's just a single wave function. That's the wave function of the universe. And then there's all these particles in addition to that. Okay. What is the wave function of a subsystem? Okay. If you do experiments, we usually ascribe a certain wave function to that subsystem. Okay. So if you do the double slit experiment, we think, the system is described by a certain wave function. Okay. So here in the Bohmian theory, there's only the wave function of the universe and these particles. So how from these entities do we get out this notion of a wave function of a subsystem? Well, there's a very natural way to do that. So Durr-Golson and Zangi introduced this. And that's just to, so suppose I have here now a system described by x and y variables, and I have an actual configuration of particles x and an actual configuration of y. So think about x of the system of interest and y is your environment. How can you define the wave function of the system of interest? Well, you just take the wave function of the total system and put in the position or the configuration of the environment. So y, capital Y, that's the positions of all the particles in the environment. If you plug in their positions, which are time dependent, so it's y of t, in the wave function of the total system, you get a wave function for the subsystem. Okay, so mathematically, you can always do that. Why is that a natural notion? Well, if you were to look at the dynamics, it doesn't matter if you express it in terms of the wave function of the total system or this wave function of the subsystem. So it's exactly the same by construction. Okay? And it's also the sort of thing you would ascribe to subsystems, okay? Like in an experiment, like the double slit experiment, okay? The wave function we ascribe to that would exactly match what's given here in this recipe. Okay. And then of course you can, so this chi of t is, it's called wave function of a subsystem or conditional wave function. And you can look at a time derivative of that wave function. Okay? So now here I've given the exact form of the time derivative of that conditional wave function. So this wave function I've just defined for a subsystem. And you see it's like a Schrödinger equation for the subsystem, and plus this extra messy stuff. Okay? But you can imagine that in certain cases this will be negligible. Okay? And so you will end up with an effective Schrödinger equation for the subsystem. Okay? For example, in a measurement-like situation, that's exactly what's going to happen. Okay? Also, it's this wave function that's going to undergo an actual collapse. In measurement situations, this wave function is going to collapse. Okay? So this is how collapse comes out from the Bohmian theory. Okay? So, in quantum gravity, so in this particular approach to quantum gravity, where you just quantize GR, you can also construct a Bohmian theory. Okay, so there's a natural dynamics for the 3 metric. It's a dynamics for the 3 metric that depends on the wave function. Okay, it's written there. And also a scalar field, there's some dynamics. And this lapse and shift, you have to make a choice, so there's no dynamics given here, okay? And so what we have according to this theory is again like a 4 metric, okay, with this 3 metric which has the Bohmian evolution and a certain choice of lapse and shift. Okay. You can already see that, well, this dynamics is not going to be trivial, okay? So even though my wave function doesn't depend on time, generically I'm going to have a time evolution. Okay. So this is, in short, how this theory solves the problem of time. So there's time evolution. Why? Well, my actual metric is changing in time. Even though the wave function is static, the wave function determines my velocity field for the actual metric, non-trivial, and will generically give you some non-trivial time evolution. Okay. So this is one of the virtues. So maybe also a drawback. So you might think, this looks very much like the classical picture of GR, the Hamiltonian formulation of GR, but there's an important difference. So in classical GR, my lapse and shift function were free. Any two choices would give me the same four geometry. This is no longer the case here. Okay? My lapse function, different choices will give me different four geometries. So I have to stick to a particular choice of lapse function. Shift function is free. Okay? So in other words, this theory breaks general covariance. Okay? At least on a fundamental level. On an effective level, maybe that washes out. So and the situation here is analogous to like in special relativity. In Bohmian theories for special relativity, it's hard to combine them, or it's hard to make them Lorentz invariant. Okay? And an easy way would be to introduce a preferred reference frame. Or there's also ways of trying to formulate Lorentz invariant Bohmian theories. Okay. But it's a question, are these serious models or not? Okay. I've written a paper on that for the people interested. So but the good things are, well, there's no problem of time. There's also no problem of space because, well, if the wave function was all there is, so it doesn't evolve in time, but also where's space in this picture? Because there was just this wave function on three metrics. What does it really tell about space itself? Okay, so is it also somehow emergent or not? We don't talk about emergence here, well, because for us, space-time is just given. There's a certain space-time, and there's certain dynamics for it. I also told you that, well, in non-relativistic quantum mechanics, you get out the usual predictions of quantum mechanics. But in this case, well, you get out the predictions of usual quantum gravity. The question then is, what are these exactly? Okay, because physicists have different ways of trying to deal with the problem of time and to try to get out predictions out of the Wheeler-Dewitt theory. Okay, so it's not exactly clear what these predictions are, these standard quantum predictions, in this context. Okay, in particular due to the problem of time. So maybe just to give an example, like this Hartle-Hawken wave function you might have heard of, it's very much studied. Okay, people try to get out predictions out of this Hartle-Hawken wave function and see if it's compatible with what we see around us or not. Like if there's a period of inflation or not. Well, from the Bohmian point of view, this wave function is out of the window. So why? Because according to that wave function, everything would be static again. So even on the Bohmian level, there would be no dynamics. So from a Bohmian point of view, okay, this cannot account for our universe. Okay? So from a Bohmian point of view, this is empirically incorrect, this wave function. But on the other hand, people study that in the context of ordinary quantum mechanics. So, in analogy with this Newtonian equation I showed you, you can also get out Einstein's equations with an extra modification, so an extra contribution to the energy momentum tensor. Okay? Which then depends again on the quantum potential. Which is kind of interesting because, well, it can show you where you get deviations from classicality. For example, you can maybe show how you evade the singularity theorems of Penrose and Hawking. Another thing to speculate about is, well, we have this problem of dark energy. What exactly is it? Is it just a cosmological constant, or what could it be? But you have this extra contribution here. Now you can start speculating. maybe this is the source of dark energy. There's also papers on that if you want. So I mentioned some conceptual problems with the theory, but there's also technical problems. So trying to solve it, trying to even make mathematical sense of it, that needs a lot of work and which hasn't been done all. Okay. So what people often do is resort to meaning superspace type models. So where you apply the same techniques, but you assume some symmetry first. So for example, you look at homogeneous and isotropic space-time, and you apply the usual quantization techniques to them, and then you get to mini superspace quantum gravity. Okay. And one way to do that is like start with this FLRW metric, where you just have 2 degrees of freedom, like n again, the lapse function, and a, the scale factor, which tells you how the universe is expanding or contracting. So they only depend on time here, and you also have a scalar field, say, for the matter, which also only depends on time. And then the analog of the Wheeler-Dewitt equation in the simplified setup looks like that. And here with alpha, is defined by taking a equal to e to the I alpha, just for convenience. So this is what it looks like. And so from here, you can easily step to loop quantum cosmology. So loop quantum cosmology, that's really the loop quantum gravity techniques applied to meaning superspace. Okay? And to actually derive loop quantum gravity, even in this context, it's a long story. But there's an easy shortcut, okay, some heuristic shortcut to get to there from the Wheeler-Dewitt equation. Okay? What you do is, well, so the first equation there is the Wheeler-Dewitt equation, so I assumed all potentials, matter potentials and gravitational potentials, assumed in 0. And the first thing you do is write everything in terms of, instead of terms of A, the scale factor, you write it in terms of A cubed, okay, related to the volume of the universe. So that's my nu. So just rewriting the Wheeler-Dewitt equation, I get something like that. And then to get to loop quantum gravity, in this meaning superspace context, you just do 2 modifications. First of all, you discretize mu. Okay. So my wave function, instead of taking a value for any possible mu, it only takes values on a discrete set of nu's. So that's the first modification. So instead of a differential operator, you get a difference operator. So the wave function only has support on discrete values of mu. And then second is this 1 over nu you see there in the front. You're going to replace that by some other function of nu. Another function of nu which has the same behavior for large nu, for large volumes, but is 0 if nu goes to 0. Okay, so this is going to be essential really to solve the singularity problem. Okay, so you, 2 modifications, you discretize a nu, and you replace this 1 over nu by b nu. So this is really a heuristic shortcut to get to these type of equations. So the resulting wave equation then looks something like that. Okay. And for that you can also play the Bohmian game and introduce a Bohmian type of dynamics. Okay, so in this case, there's an actual scalar field, there's an actual FLRW metric, and the way they evolve is, well, the equation for motion for phi is the same, more or less the same as before. But this nu, or A, okay, the scale factor, is now changing stochastically. So in this Bohmian picture, what is the A doing? Well, it might, in a certain amount of time, jump to another value. So discretely, at random times, it jumps and gets bigger, okay? So there's no more continuous evolution of my scale factor, so there's no more continuous expansion, say, of my universe. It's going in discrete steps.
So you look at these by hand, right?
Yeah, or what do you mean exactly?
I mean, look at the discreteness of the volume of the
No. So I just use this discreteness of the Wheeler-Dewitt equation. So that's my starting point. That's what ordinary loop quantum gravity gives me. Suppose I start from that and just make a Bohmian version of that. And I'm naturally led to this kind of dynamics. It's a type of dynamics Bell introduced like for QFT on lattice. Okay. Again, by looking at the continuity equation and having some process that preserves the usual quantum statistics. So I said that there is no problem of time here because, well, there's an actual metric and that evolves in time. But it's also interesting to compare to other versions, other ideas to solve this problem. Okay. So, and one is to somehow argue that, well, one of the variables that appears in the Wheeler-Dewitt equation is like, that's my time variable. Okay, so like in Charlotte's talk this morning, when you were discussing loop quantum gravity, you just said, phi is taken as a scalar field. Okay? And then you can ask the question, why do I take phi as a scalar field and not mu? Okay, what's exactly the choice for that? Okay? Or here, like I have my Wheeler-Dewitt equation, I could take phi as my time parameter and massage my wave equation in the form of a Schrödinger-like equation. Or I could take alpha as my time parameter. So which one do I take? Okay. So in the Bohmian case, I can also talk about clock variables, okay, which capture the time evolution. Okay. But there it's unambiguous how to do that. If I have one of my degrees of freedom that's changing monotonically in time, I can use that as a clock variable. And of course, you can have different clock variables. And I can also know the relation between the two. Okay? If I don't have these resources, so if I just have this wave equation, which one do I take as time? And you can imagine that some conclusions are going to depend on which choice I take. Okay? The setup of my Hilbert space, the question about singularities, they might very well depend on these choices. Okay? And one of the other main approaches to the problem of time is this, what was just heard, is this semi-classical or WKB time. Okay. And here, this is also a very rough sketch. So what we have is the wave function. And perhaps after decoherence, it's of a form where you have psi 0 and phi. And psi 0 is a semi-classical wave function. It's well approximated by the lowest order WKB approximation. And what's then considered is like a classical solution for my tree metric given by this S0. Okay, so these were the rays Klaus Kiefer was talking about. Okay. And then what you do with this classical solution is you plug it into the wave function. So you plug it in here. And then you can take a time derivative of this object and under certain approximations get to something which looks familiar, which is just a wave function, say in this case, for my scalar field, moving in an external classical background. Okay. So in here you might worry about how do I exactly motivate that? Okay, so how do I suddenly end up with this time evolution? Okay, so what motivates this classical solution in the first place? Which classical should I use? Can I have also a non-classical solution? And why should I plug it in the wave function? But these steps, well, they would be very well motivated within Bohmian mechanics. Okay, but within Bohmian quantum gravity, that's exactly what you would do. Okay? So in Bohmian quantum gravity, to get a time-dependent wave equation, that's exactly the steps we would follow. Okay, why? Well, we have an actual trajectory for the scalar field and the 3 metric. So that's one part of the ingredient. So this classical trajectory, we have that in the theory. And then this kind of object here, that's just a conditional wave function. That's the wave function of a subsystem, according to the theory. Okay? So that's also derives naturally. Okay? And this is the wave function in which I can express my dynamics for my Bohmian scalar field. So that's why it is relevant. But also it gives you like other type of approximations, okay? So these Bohmian resources don't stop with semi-classical, in the semi-classical setup here. Okay, for example, this background I have here could maybe also describe quantum mechanics. So this background that appears here could be a non-classical solution, and so on. And actually, the first people that gave the dynamics of Bohmian quantum gravity, it was not people thinking about the foundations of quantum mechanics. It was actually people working on this semi-classical WKB prime. Okay? And what they did was, they wondered, and rightly wondered, why do I actually use this classicality assumption in this derivation? I can also do everything without assuming that. And what they have in the end is just the Bohmian equations. Okay, so if you give up this classicality assumption, from this WKB program, you're just automatically led to the Bohmian equations. So this was 2 independent papers, Greenside and Badmanaban. They both just gave the Bohmian dynamics without knowing this was actually a Bohmian dynamics. And then, of course, Bohmian quantum gravity was up in the air at the time. I think mainly inspired by the semi-classical approach. Because then, like in the early 90s, a whole bunch of people independently came up with the Bohmian formulation. Okay. So, and you can do all kinds of derivations, right? So using this conditional wave function, you can try to develop a quantum evolution for fluctuations onto a classical background, okay? So very much the way Klaus Kiefer described, you would do basically exactly the same. But you can also see, when the approximation holds, get another way of getting higher order corrections, and so on. For example, you can, very shortly I'll say this, so you can get like semi-classical theories where you have back reaction from the quantum stuff onto the classical stuff. Instead of having like an expectation value, which you would usually do in quantum mechanics, so you can use, again, the Bohmian resources to have like the actual scalar field source, say, classical Einstein field equations. Now to these vacuum fluctuations. So a lot has been said about this already, right? So they're important in the early universe and the late universe. Okay? So in the early universe, there's these seeds of structures, okay, like galaxies and stars and so on, which are very much desired. Okay? And in the late universe, people have worried about these fluctuations might lead to so-called Boltzmann brains. So brains popping out of nowhere with similar memories and experiences as you have now. And for some reason, they're not desired. I'll get into that in a second. So first, in the early universe, what's the story? You've heard it before. So the universe is going in an accelerated expansion, and so everything is driven to homogeneity. And you have a scalar field, the influence field, driving this expansion, and so everything becomes homogeneous, and so the only thing that remains is vacuum fluctuations. And these vacuum fluctuations are described by some quantum state, Bunch-Davis vacuum. And at some point, these fluctuations, these vacuum fluctuations described by this quantum state, become classical. And these then source the matter fluctuations, which eventually give rise to the structures you see today. And they also leave an imprint on the microwave background. So the problem here is that, well, the state is homogeneous and isotropic, okay? And how can it give rise to something that is not homogeneous and isotropic? Okay. And often this is seen as like, this is an instance of the measurement problem, okay? Because, well, how can you get from a symmetric state to an asymmetric state? Well, a measurement must have, a collapse must have happened, okay? But when exactly does this collapse happen? That's not clear, that's the source of the measurement problem. So in what's nice to see in these cosmology books is that cosmologists acknowledge, this is an instance of the measurement problem, okay? In QFT books, you usually don't see the measurement problem acknowledged, so this is nice to see. So but from the Bohmian point of view, well, you can also do a Bohmian description here of these fluctuations. And what you see is, at late times, so first of all, let me say, the actual Bohmian field describing these fluctuations, it won't be homogeneous or isotropic. Okay, so this is what breaks the symmetry. And also it's going to behave classically at later times, okay, exactly when you would expect it. Okay. And in our analysis, we didn't appeal to decoherence, but this would be compatible with decoherence. So with the stories David Wallace and Klaus Kiefer told, if there's decoherence of the expected sort, that wouldn't destroy the results. Okay. And the comparison can be made like suppose you have a single particle which has a spherical wave. So perfect spherical symmetry. And suppose you have an array of detectors placed around it, also symmetrical. According to standard quantum mechanics, the collapse would break the symmetry. So one of the detectors would click and the symmetry is broken by the collapse of the wave function. Okay. So in the Bohmian case, what's going to happen is this particle is just going to travel in a straight line in a certain direction. Okay. So the symmetry is broken. Actually, it's also a classical trajectory, and it just hits one of the detectors, and that's the detector that's going to click. Okay. So in the late universe, there's a similar story. So now the expansion is driven by dark energy. Okay. So in the very late universe, what's going to happen is that also all matter is going to be driven to homogeneity. Okay, first black holes are going to form, they're going to evaporate, and so on. But at the end of the day, everything is going to be driven to homogeneity. The only thing that remains is vacuum fluctuations. And here the thing is, these vacuum fluctuations could take any form. Okay? It could be tables and chairs popping up. Okay? And of course, the bigger the fluctuation, the less likely. But if you have eternity to wait, well, eventually this is bound to happen. And what's also going to happen is then that observers are going to pop up. Okay? Observers like us, okay, it might be short-lived or they might be bigger fluctuations so that they're longer-lived. Okay? But this will happen again and again. Okay? So if you look at over the whole course of the history of the universe, most of the observers within the universe will be these Boltzmann brains. So we have a short period in time where we have ordinary observers that came out of evolution and so on. And in the late universe, you will have these Boltzmann brains popping up over and over again. And then the argument goes, that's described by people like Susskind, Albrecht, and Carroll, and so on. Then the argument goes that we should expect ourselves to be typical observers. But if a typical observer is a Boltzmann brain, then we should expect ourselves to be Boltzmann brains. But we are not. So the conclusion then is, maybe there's something wrong with our cosmological theories. Okay? maybe we have to amend our cosmological theories so that we don't end up with these Boltzmann brains. Again here, yeah, what's actually the reason why we see this vacuum as this fluctuating soup where everything comes out? Okay, does it mean that the wave function has some support on these configurations, or does it mean that, or does it come out because the wave function collapses? When does the wave function collapses? Okay, so here again you have the measurement problem. So in the Bohmian case, well, we just attack this premise that, well, there's going to be these Boltzmann brains forming. In the Bohmian case, nothing special is happening. So in the late universe, what's going to happen is that everything actually becomes static. The Bohmian configuration is not going to evolve in time. So it's not so that we have these random fluctuations appearing over and over again. So by the way, if you're interested, Sean Carroll discusses this problem from the point of view of many worlds theory, okay, and also gets to the conclusion about this wave function at late times, it's a quasi-static state, so nothing really exciting like these fluctuations is happening. So finally, I want to say something about space-time singularities. So as I said, classically, they're unavoidable, like a Big Bang singularity is unavoidable. But the question is, what happens in quantum gravity? Okay. Are these eliminated? Okay. But if the wave function is all there is, okay, you would think, if I have a well-defined solution to my Wheeler-Dewitt equation, then I'm fine, right? On the level of the wave function, there's no singularity, so what else should I worry about, okay? But people usually want to say more, okay? They want to, I'm not sure what exactly they want to say about spacetime and singularities, so they want to maybe say, spacetime somehow emerges, and maybe the singularities emerge with them, okay? But the thing is, people have proposed different criteria what it could mean to solve the singularity problem. Okay? So people have sometimes said, okay, I have a singularity when my wave function has support on singular metrics. Okay? Or my wave function is peaked around singular metrics. Or maybe I have singularities when my expectation value is singular. But neither of these is really satisfactory. Okay, for example, the first one, psi has support on singular metrics. Well, the set of singular metrics has basically measured 0, right? So in the usual Hilbert space sense, it doesn't make sense about looking at something like that. Or like the last one, if on average your wave function, if on average you don't have a singularity, what does it mean for our universe? Okay, we have a single universe. Does it mean we have a singularity within our universe or not? So one thing we did once was propose an alternative criterion and look at the flux. Okay, so if you have a probability flux, you can look, is there a probability flux into singularity or not? So this is kind of related to the Bohmian theory, but could also be seen independently. So within ordinary quantum mechanics, okay, this is some natural thing to look at. Is there flux, probability flux into the singularity or not? If there's no probability flux into the singularity, there's no singularity. So, for example, if you look at the Coulomb potential in the Dirac equation, okay, you can question, do I have a singularity here because of this singularity in the Coulomb potential or not? Okay. And the wave function is actually infinite, I think, at the singularity of the Coulomb potential. But there's no flux into the singularity. There's no probability density leaked into the singularity. So this seems to be a nice criterion to look at. But anyway, so there has been a lot of work on this, right? So and one type of work in particular is that that of people like Ashtekar, Singh, Kurichi. Okay. And they looked at Wheeler-Dewitt theory and also loop quantum gravity and looked at the problem of singularities. Okay. Okay. And they looked at this peak criterion. Okay, so I have a singularity if my wave function is peaked around the singularity. And also they use phi as time. And they found for a class of wave functions, okay, that the Wheeler-Dewitt theory gives singularities, whereas loop quantum gravity would not. So they do it for a particular class of wave functions, which are semi-classical at late times, so at large values for phi.
But there are many cases where we can avoid singularities. So, of course, if you choose to go singularities.
You mean for other wave functions, or?
Yeah, we have studied many examples and models where ideally by the criterion that psi goes to zero for classical singularity, that this can be implemented.
Yeah. So I know that's why I said there was a large amount of literature, so I just picked out these.
Also, can read all the singularities, but because they exist, those that avoid
So, well, the main point I was to make is that in loop quantum gravity, they think the problem is completely solved. Okay, and they show that just for a particular class of states. But of course, you have this question: what exactly do you mean by singularity? And also, people disagree about that.
It's criterion 67 that we don't know exactly what the wave function is, but if it's definitely zero at the basis where the classical singularities are, then you would say there is no classical singularity.
But if that's just it, you could say, the point where it's zero, I put my wave function to zero. I get the same state in any type of Hilbert space. Okay. The value of the wave function at a single point doesn't matter, right? In a certain region, but then it has to be. Yeah. Well, so dropping to zero. Yeah.
So you cannot use a classical wave vector. That follows that you cannot go there because that it spreads or goes to zero. So if you look, say, graphically, so the wave packet follows during the Big Bang, but before that it just goes to zero. And so the classical evolution stops before.
So if you talk about this evolution, it seems well compatible with like looking at flux then more than because the wave function actually is static. Yeah. That I like more than No, but so I just brought this up to make the comparison. Like, what does Bohmian quantum gravity say in this case? In the Bohmian case, but also, first of all, there's no ambiguity. What it means to have a singularity is just when your actual metric is singular in the classical sense or not. Okay. And then you can just look at solutions and see in Wheeler-Dewitt theory, there may or may not be singularities. It might depend on your wave function. Okay. It might also depend on your actual initial condition for your actual metric and scalar field. But also interesting maybe is that in the loop quantum gravity case, you can actually show that there's never singularity in the Bohmian case, okay? So whatever the wave function is, there's just a dynamical obstruction. So I said there's this hopping of the scale factor, okay? So in the Bohmian picture, it's undergoing jumps, okay, from one value to the other, okay? There's never, it's just impossible to have a hopping just all the way to zero. Okay, so in this way, singularities are avoided, and that's for any wave function. Okay. And also without singling out a particular time. So in the Bohmian case, I don't have to say, my scalar field is the time or my scale factor is the time. Okay. So let me end here. Thank you.
Thank you. So maybe this is a more general version of Klaus's comments right at the end. I think when we discuss the case of space-time singularities, also for loop quantization, I think you're a little bit uncharitable. It's true there are different criteria to be used. There's some discussion to be had which one could be used. But still, I think there is a reasonable case to be made that on reasonable notions of singularities, we have resolution, sufficiently generically that.
Which one? Which one do you take, like, to really capture the notion of singularity?
This criteria that the wave function is zero, for instance.
But it has to be more than just zero, right? Because I can choose the value of my wave function on a set of measure 0 to be whatever I want. Okay. In any L2 sense, that's not going to change my wave function. It's going to be the same.
Yeah.
Quantum state. So it has to be more. Maybe it has to be sufficiently fast. But then you can worry how fast. And
yes. But I think on a reasonable criterion like that, you could make the case that also in, let's say, non-Bohmian loop quantum gravity, there's singularity resolution.
Well, you can say whatever you want.
No, I mean reasonably.
So like from a practical point of view, yeah, I like these kind of arguments, okay, but I want to have something more. Yeah.
From a philosophical point of view?
No, I want to derive that from like first principles. Okay, so my theory is this, and like for all practical purposes, people try all kinds of things, like Wheeler-Dewitt theory, and that's fine for practical purposes. But at the end of the day, I will also want to have a justification of why do you do that exactly. So like the collapse of the wave function is also fine for practical purposes, but at the end of the day, I want something more, and like.
So is the claim then that on non-Bohmian loop quantum gravity, the best case for singularity resolution you can make is of that practical type? Say like, here's a bunch of plausible practical considerations why we shouldn't be worried about that. Whereas in Bohmian loop quantum gravity, you can see it from, in a more principled way, that there's nothing to worry about.
Well, it's also a bit different, no? Like in GR, there are these space-time singularities, and it's clear, wow, that's where the physics breaks down. You cannot evolve your solution further. And there's nothing like that going on here, right? If I have a solution to my Wheeler-Dewitt equation in loop quantum gravity, if that is well defined, could I ask more? Okay? Then it seems like I don't have any singularity problem, whatever singularity I mean, okay?
Way, not just
No, but then it's, you're talking about something emergent, okay? So if spacetime is emergent from that wave function, can also singularities then emerge? So I don't know, there's a lot to say about this. Prima facie, there seems to be no singularity problem just because if the wave function is well defined, there's no breakdown of my physics anywhere or something like that. So what is this talk about singularities then really about? And if there's ambiguity in this notion of singularity, why should I worry about this? Okay? Different notions if you have different notions, one notion might lead you to the conclusion, there's a problem, or another notion might lead you to there's no problem. I don't know.
I'm not confused on this issue because in loop quantum gravity, singularity resolution is from first principle. I mean, even if in loop quantum cosmology, then people try on different space-time, test this on different space-time, but you can get it from first principles. So you cannot have any curvature singularities if you are working with loop quantum gravity.
And what do you mean by similarity? I guess you would refer to the volume operator.
No,
Oh,
I
okay.
refer to, because the volume operator itself is not enough, I refer to the quantum dynamics. I mean, because the discreteness that you have with quantum gravity is discreteness in space-time, not just a discreteness in space. So, I mean, if you do things from scratch well, in the full theory, you have, I mean, of course, here you're doing
But like here, what would I say? When do I have a singularity given this equation? What is the first principles in loop quantum gravity that tells me I don't have any
Well, the
singularity?
thing is that here, this equation that you have, that I don't even...
Loop quantum cosmology,
Yeah, okay, so the thing is that...
no potentials.
Yeah, but as you said, I mean, this kind of equation that you are writing here, it's... can you break it? Well, okay, so is this...
Just a scalar field coupled to Friedman, Robertson, Walker, and nu is proportional to a cubed.
Yeah,
Okay.
okay.
So and that's discrete in nu and continuous still in phi. And b nu is just a function of nu.
Okay, so
Like this, it's the same equation. Well, you had one implementation of this equation earlier this morning.
So I suppose this is just the standard...
Yeah, the Wheeler-Dewitt equation.
Okay, so the dynamics of the quantum gravity is not equivalent to the Wheeler-Dewitt also.
There's more than Wheeler-Dewitt?
Yes, in the sense that you can show that because of the loop quantizations, you have something that is inequivalent to Wheeler-Dewitt. Well, it's Wheeler-Dewitt.
No, it's not. Sorry. I thought this was also called the Wheeler-Dewitt equation. It's loop implementation of Wheeler-Dewitt.
Yeah, but so we are getting into details, but what I was trying to say before is the fact that if you start with the loop quantum gravity, even if you do loop quantum cosmology and so on, you never have any singularity in the curvature because this is embedded in the structure of the theory. It is a gauge theory in which you quantize gauge variables, in which the fundamental discreteness is in the Lorentz group. So you have maximal curvature, and so no possible divergences in the curvature. On the other hand,
so here it would be the question: can I have a Big Bang or not? Like,
you cannot have a Big Bang.
Yeah.
Because you cannot have a curvature going to in any theory of gravity.
and so how do I extract this curvature from the wave function now?
How do I...
Yeah, because that's your singularity criterion, like no blow up of curvature.
What I'm saying is that, I mean, here you have things written in a very compact manner, but when you start from scratch in the theory, you start from the full equalization of the full space of the theory, you realize, I mean, if you do...
But we should also only worry about the end product, right? So if that is the theory, not how you interpret it, or...
I want to say something. Let me accept this part, okay? And then saying you have accepted that there is no curvature glow up in quantum cosmology. I wanted to say you also have no singularity resolution in Bohmian mechanics by itself, without the quantization, isn't it?
Yeah, I start from this equation that comes from loop quantum gravity.
Yeah, well, what
this wave equation.
I'm saying that even if you don't throw into this quantum gravity, you already have singularity resolution in Bohmian mechanics.
So I have a Bohmian version like for the usual Wheeler-Dewitt equation, and I also have a Bohmian version for loop quantum cosmology.
Yeah. So
But like in the first case, there might be similarities in the Bohmian theory, and here not. It might be that there's a Big Bang, or
because
in usual Wheeler-Dewitt theory, right? Not
using Bohmian mechanics, there are this word like of Nelson
Yeah.
in which you have avoidance of this.
I have for certain wave functions, not in general. For certain wave functions, you have avoidance of similarities, or for certain initial conditions. Okay, so it very much depends on the wave function. For some wave functions, for any initial Bohmian configuration, there is no singularity.
So when you talk about the wave function here, is the wave function, so this depends on the type of wave?
This is the pilot wave, yeah, exactly. And the wave function we just take from what usual quantum people do, right? So loop quantum gravity people like you provide me with this wave equation, and then...
Yeah, so what I was trying to say is that, so my expectation was that you could, I mean, this is of interest independently of the singularity resolution, because singularity resolution is achieved on one side and on the other. So
but like all the ingredients in loop quantum cosmology that hint at singularity resolution, okay, these are also exploited in the Bohmian version of that, right? So that's like this factor B nu, that is this function of nu that's zero scale factor, but goes like 1 over a cubed for larger a. That's really essential, like to also show that in the Bohmian case there's complete singularity resolution. So these things, these aspects of ordinary loop quantum cosmology are really important to us. But because I have like a precise criterion of what a singularity means, I have like an unambiguous answer. I was just saying, like in the literature, there's all these notions flowing around. There's also notions I haven't mentioned. Okay, you know this better than I do. Okay.
That was lovely talk, thank you. Let me ask about Boltzmann domains. So I'm puzzled about how that's supposed to be avoided in the wave framework. So a way of putting the Boltzmann domain problem into canonical cosmology is something like the universe, future asymptote, city space. If I consider the kind of static wedge from the city space, then its quantum state, once I trace over stuff outside, it is thermal at a very, very low but finite temperature. So it will assign a very, very low but finite one-squared amplitude to particle configurations corresponding to the presence of the Boltzmann domain. And an empirically adequate Bohmian theory for this is going to have to reproduce the Born rule with respect at least to the distribution of macroscopic matter. So if the quantum state assigns a very, very small but non-zero amplitude at any given time for a Boltzmann range present, it seems that the Bohm theory is going to have to assign a very, very small but non-zero probability for there being a Boltzmann present at that time. And then if I just iterate that argument indefinitely into the future of Boltzmann range. So I'm not understanding how the problem is dissolved here.
Yeah, so you're exactly right? The whole story you told. Indeed, there's a probability that a Boltzmann brane forms. There's indeed a probability that there's a chance that a Boltzmann brane will form within our observable universe. Okay. And if it forms, it will be still static and stuck with a thought, and then you might worry, I might still have a Boltzmann brane, rightly so, and then maybe you can argue, but this is going a bit further than, maybe this is not a function in the brain, and so this typicality argument, I shouldn't use that. I don't have much to say about that. But you might, there's like, you have this agreement with quantum mechanics, and so you should expect the Born rule, and you might think, why isn't my Bohmian configuration fluctuating? Okay?
Exactly.
And the reason is that no measurements are taking place. So maybe to make a simple comparison, if I have an electron in the ground state for the hydrogen atom, my Bohmian particle isn't going to move. It's also going to be static. But suppose I measure where the electron is, and I do it over and over, I do measurements of where's my electron, it will change. So the Bohmian theory will say, it will change. And so here you get out the Born rule again. But if you don't do the measurement, and that's crucial here in this context, so in the late universe, there's no measurements, no process like measurements taking place, so it stays static.
Yes, I'm worried that, I mean, the devil may be in the details here, but I'm worried that if you actually do the dynamics of thermal state, it's going to include a whole bunch of just things that in a Bohmian theory are going to be described as spontaneous transitions. It's not obvious to me that I should just have staticness in that state.
Okay, so what we did was just look at like a Bunch-Davies vacuum, right, and do the analysis for that, so...
Right, so Bunch Davis strikes me as plausibly right. If you had a particle version of Bohmian, and you had a Bunch Davis vacuum, I can certainly see that you might be fine. But of course, the quantum state in this situation is not Bunch Davis. It's not in the wedge. It's thermal. Or do you want to say that it's Bunch Davis across the whole?
Yeah. And this is also an approximation, right? I don't know what like a full quantum theory for gravity would say is the state there. But suppose I have a ground state in whatever theory. The Bohmian dynamics is always trivial. Everything is always static, so there's nothing.
Right, the thermal state. I mean, I guess that's the big question, isn't it? So you can't. If I'm.
But here you obtain it by tracing out, right? So like. In Bohm on a fundamental level.
So there's two ways you could do the quantum. You could think about quantum mechanics here. I could think in the sort of foliation appropriate to Bunch Davis, but in that case, of course, that's not. I mean, that's not a ground state. I haven't got a state on that foliation. I haven't got a steady Hamiltonian. The system is evolving, particles being created. I could be thinking in terms of the kind of the static coordination of the this interface, but in that case the quantum, and then I do have a ground state, but the system won't need it. The ground state is singular on the horizon. The system needs to be a thermal state, and it's not obvious to me how. I mean, it's not obvious to me it won't be static, but it's not obvious to me that a Bohmian description of the thermal state is not going to involve temperature fluctuations.
So you're also saying that like maybe if you have a particle ontology, so because also the analysis was done with a field ontology, and so with are you saying maybe with a particle ontology you might have these fluctuations?
It's actually slightly more obvious.
Because expansion produces.
Yeah, it's actually anything slightly more obvious to me that there'd be a problem with a field description. But I guess however you fill in the details of a Bohmian field theory, it's going to have to reproduce the Providence distribution for the macroscopic distributions of particles just to empirically adequate.
But that's only upon measurements, right? For measurements you won't have psi-squared distributions in the Bohmian case. So what it's doing in between measurements, well...
Sure, so, well, I suppose you're going to have one off, but then you can believe Jimmy says no transitions. It's just not, it's not at all obvious to me that there shouldn't be dynamical transitions in a thermal state in Bohm's theory, even if I leave the theory alone. It's not obvious to me there shouldn't be. I mean, if you look at some of the, well, if you look at something like the Deriving model, as if I remember it correctly, its vacuum would be perfectly stationary for free particles, but I absolutely have quantum transitions. I guess this is a field model that's deterministic, so you haven't got that kind of phenomenology.
Yeah. So I see. Yeah. Like with the Deriving model, if just Minkowski space-time, the vacuum state will also be, everything will be static. But I'm not sure what would change in an expanding space-time.
That's not obvious to me. I mean, the Deriving model, I mean, I hesitate to disagree with you on the Bohmian version of quantum field theory, but my understanding of the Deriving model is, if I have free field theory, then sure, the vacuum just sits there. But if I have interactions, then I'm going to have stochastic processes of particles coming from distant disappearing. I mean, they advance it as an advantage of the theory that it gives a physical realization, which is the heuristic idea that the vacuum is a sort of buoyant sea of particles coming in and going. Now, that's happening in their framework because they've got a stochastic rule that complements the guidance equation. And I guess your framework is field indifferent deterministic, so that argument doesn't work.
No. But even in that case, in that stochastic case, in Lorentzian spacetime, I'm pretty sure that for the vacuum state, nothing moves. But for an expanding space, I don't know. That I don't know.
Well, it gets into the details, and I can get the details. Let me just say, it feels to me that I'd like to hear more about just why, just what quantum mechanics is supposed to be that gives me a confidence I'm not going to be seeing state transitions at the level of the particle distribution in the Bohm framework. I can believe it is here, but it's not clear to me.
And I can't guarantee that for any Bohmian version this will happen. That's for sure.
Yeah,
nonetheless, there seem to be good reasons to think that such decoherence occurs or exists.
Yeah.
I guess, to me, it feels like a bit of a strange coincidence that decoherence is exactly the kind of decoherence you would need for a European version of classicality is present, but plays no role at all in the version of classicality. So I wondered, in your approach, do I just have to accept that as a brute, unexplainable coincidence, or is there some way to understand it better?
I think, like at the end of the day, like if you were to compare like decoherence-based stories about what's happening with these fluctuations, the only difference is going to be, I think, when does the decoherence kick in? So in the Bohmian picture, I will have classicality even before that. Okay, and then decoherence kicks in, but doesn't change anything to this classical motion.
Right, but I mean, my worry is that the decoherence looks very much like the kind of thing you would expect to be involved in the version of classicality, and yet your account is totally irrelevant. And that just seems like a strange coincidence.
Well, it's going to be relevant at the end of the day, right? If you want to have like detailed analysis, there must be, if there's no decoherence of the right sort, it would also destroy this Bohmian first result, like not worrying about coupling to other degrees of freedom. So you have taken a simplified approach, right?
So it is in fact
What? Yeah. But decoherence doesn't have to happen early on. In the early stages of the universe, it can happen later. But still you can tell the story about, this is how it became classical. And like it's like with the spherical wave I was saying, okay? In the case of the spherical wave, maybe it's expanding for 1 million light years, okay? And the detectors are there at 1 million light years. My Bohmian trajectory is always going to be a straight line, so always classical. And decoherence is only going to kick in like after this 1 million light years where the detectors are, because of the coupling to the detectors.
right, so decoherence is part of the story, but maybe not in the early universe?
Yeah.
Even though it's present in the early universe?
So if there's decoherence of the right sort, of the sort people expect to happen, okay, this is not going to change the trajectory. Okay, it's only, yeah.
I mean, just as a comment on this, this came up a little bit in my talk this morning. This is this issue of the fact that sometimes I have autonomy just because there are no degrees of freedom to come. So in one sense, there absolutely is decoherence in the story you described, in the sense that I don't have any interference between branches, so I can define a consistent history of the branches. And in that, and I think that minimal sense of decoherence, i.e. the absence of interference, is something that Bohmian mechanics needs, because it's what explains effective collapse and says that I don't need to worry about the empty waves coming back and re-interfering with the wave packet that's guiding my particles. But that's not environment-induced decoherence, it's not happening. The interference isn't being suppressed by entangling other degrees of freedom, it's just not being generated in the first place. So this is a terminological issue, just what decoherence means.
Yeah, but even for like a single particle in the Bohmian case, I could say, in your terminology, I have decoherence because suppose I have a plane wave, my Bohmian trajectory will be a straight line.
Yeah.
And of course I can carve out the wave function in like Gaussians, and like one of these Gaussians could equally well describe this.
And if you write down a decoherent history family based on coarse grain position or phase-based chunking, it will obey, for plane wave dynamics, it will obey the decoherence condition. Now, it won't do if, of course, I'm doing it for a two-slit experiment. And indeed, in exactly that situation, because I don't get effective wave function collapse for the Bohmian. And nor we want to, because we want to reproduce the interference effects there. But effective collapse for the Bohmian this isn't in any way a problem for plane, this is just descriptive. Effective collapse for the Bohmian requires decoherence in the decoherent history sense of decoherence, because it requires interference suppression. Sorry, interference disappearance, but it might be the interference doesn't need suppressing because it wasn't appearing in the first place. Plane wave would fit that, so just
but here you might have a bigger worry about different families, incompatible families of decoherent histories, like in the simple situations.
Absolutely. Yeah. You might, so in sufficiently simple dynamics, you might find that that's not enough to pick out interesting structure in the kind of way that a decoherence-based approach would. In Bohmian's getting by fiat because of their anti-associated to the invariance.
So I just made this point about decoherence. I didn't use it, but it's compatible with that. I'm not disagreeing with it.
But it's not just that it's compatible, but it's more that it is in fact playing some role.
in the sense David said, yeah, then. But then, like, what's really going on is, like, suppose I have this single particle moving along a straight line. So the wave function, like determining the velocity of that particle, it's only relevant near in the region of that particle. So I can forget about what the wave function is doing away from the particle. So in that sense, I can have like an effective collapse. Okay. And if you want to call that decoherence, okay, fine.
I mean, it's good. It should be involved because, as I say, I would be a strange coincidence that I know religion. So that's good reason.
I mean, it's a terminological difference actually between how different communities in decoherence would use the word decoherence. So for the sort of Zurich groups, then the decoherence definition is environment induced suppression of interference effects, whereas for the sort of decoherent histories crowd, then decoherence just means no interference as realized from existing history conditions. And environment, entanglement environment degrees of freedom is the normal dynamical mechanism that is decoherence, but it's not definition of decoherence. And that's not a fact disagreement between these groups, it's just terminology.
Next question from Martha.
I would like to ask a question on the use of clock values in Bohmian quantum mechanics, because at certain point you say like, I mean, they're unambiguous.
Yeah, I went very quickly over that, right? So
Yeah, but I didn't get why.
Well,
I
it just-
didn't get what's
like in a classical theory, okay, and there's time evolution of all your variables. It's clear what on a theoretical level what can be used, which variables can be used as clock variables. If you have one variable that is monotonically increasing in time, or moving monotonously, I can use that as a clock variable. Sorry? Yeah. I need change, right? I need something changing. Okay.
Yeah, but you said monotonically increasing in time, you will use the clock.
But like in so Newtonian space-time, I have time, okay, and then I have clocks in my Newtonian world, right? Like actual physical systems which have positions which change over Newtonian time.
No,
Okay.
you wanted to define the variables that they use as clocks in.
So I wanted to make the distinction between what people usually do. They have all kinds of ways together, right? But it seems often to me that they just postulate variables as clock variables. So they have their Wheeler-Dewitt equation. Let me take this variable as clock variable and express the other variables relative to that clock variable. Which variable do you take as clock variable? In the Bohmian case, it should be unambiguous what you mean by clock variables. It's the same as what we do in Newtonian theory or ordinary GL.
But I mean, I don't see what this solution to the problem of time.
No, this has nothing. So I was making a comparison to one approach to the problem of time. So if you get Bohmian mechanics, so one approach to the problem of time is to say, some of these degrees of freedom that appear in my Wheeler-Dewitt equation, so even though my wave function is static, some degrees of freedom I can identify as clocks, and I can express the other variables as changing relative to this clock variable.
But that's what it's usually done.
Yeah.
So what's the difference with what you do?
But so here there's a worry then, like, which variable do you take as clock variable? Okay, so at the end of the day, nothing is changing because this wave function is static. And why can I promote one variable to a clock variable? What happens if I promote another variable to a clock variable? Okay, and you might see, you can see that you're going to end up with different theories if you promote different variables to clock variables. Your Hilbert space will be different. You will have different conclusions about do you reach a singularity or not. So all within the quantum framework. So suppose I have two scalar fields. Which one do I take as a clock variable? And the Hilbert space structure that's associated with that will also be different. Okay.
But then what's the advantage in the Bohmian field?
Well, if you want to talk about clocks, there is no ambiguity because what are clocks? That's the same as in classical physics.
Well,
Yeah,
in classical physics, you just say like you have time. So class are like the measure of something that measure time.
Yeah. So you have something that's changing, like the hands of a clock. Okay? Something is changing. I can express the motion of something else, the motion of my train, say, with respect to the moving of the hands of the clock.
And actually, I see the difference.
But is it that your classical, is it that your clock variable is a classical variable?
What do you mean by classical variable? It's not. It's the Bohmian variables I use. Okay? So it's Rovelli's. So Rovelli's, what's he called? Partial observables. So that's exactly classically. Yeah, that's exactly how you would describe clock variables. Okay, and that is just carried over in the Bohmian theory. It's a different dynamics, but you have these variables changing over time. Okay, so you have matter changing position over time, and so that change of position can be a reference, can serve as a clock.
It was just as another approach to.
What?
So it was just like the fact you just pick a clock variable. I mean, I speak.
Like in the Bohmian case, I can also, there's different clock variables I can choose, right? But if there's one degree of freedom being static, that's no clock variable. I can use different degrees of freedom that change in time, okay, and express the other variables with respect to this clock variable. I can move between. If I show you some math, it will probably be clearer. But
We can discuss it later.
David?
So this is just to get some technical clarification on something we had earlier. So there were two pieces I didn't quite see how they fit together. You said that the four-dimensional space-time I get out from the guidance equation depends on my choice of Laplace function, so I don't have Lorentz coherence. But you also said that the guidance equation gives, up to quantum corrections, gives me out the Einstein field equations. So I'm just wondering where's they're going to be some dependent, given the first thing, there's going to be some dependence of the quasi-classical, of the Bohmian dynamics on the Laplace function. It's not showing up in the guidance, is it showing up in the quantum correction?
I'm not sure I've written that explicitly. But so, so implicitly there's a foliation there.
Yeah.
Okay, I can only express this Q, this little q, with respect to that foliation. Okay?
Yeah.
So another way to see it is like ordinary GR, it's foliation independent. So if I have my original 3 metric, it doesn't matter how I evolve it to a future hypersurface. Okay? That amounts to the choice of Laplace, really.
So the quantum potential is foliation dependent, and so that's
Okay. So you see a y and a t there, right, as arguments. So y and t is with respect to one foliation.
So how, in principle, that gives an empirical route from the successive GR to constraints on what the Bohmian Laplace function is. How stringent are those constraints?
Well, usually these quantum effects of dq we don't see, so as soon as that is gone, you have ordinary GR and general covariance.
Because in a certain sense, the details of the dynamics under this quantum contribution are one of the most interesting things here, because that's a signature. But in one thing that seems interesting is it's striking that the signature we would be getting from the quantum corrections is a direct signature of the true foliation, which differently from sort of extant Bohmian field theories, which are generally not Lorentz covariant, but which the Lorentz covariance violations are visible. This is like principle testable.
Yeah, so in special relativity you have that, okay, the simplest Bohmian formulations are also not Lorentz invariant, but it doesn't show up in the statistics. Exactly. It's washed out in the statistics. Yeah. So in here, wow, it's probably also going to be the case, these need to be filled in, that it's going to be washed out in the statistics.
Oh, well, that would be,
yeah. But,
would be very interesting to check if that's true. Because it seems important to check if that's true. Either way, it's interesting.
Yeah.
I mean, either it reproduces what we see in the relativistic case, which is a conceptual puzzle about both theories, or it doesn't, in which case it's something really interesting.
Yeah, well, there's a whole story I haven't told here about probabilities, right? As you can imagine. And you have to do some work, so, and the basic ideas are there, but the worked out examples don't exist. Because this wave function is not normalizable, you have to say something. Well, we know what to say.
Well, I mean,
it's a long story.
But after all, we move, as I understand it, we move from Wheeler-Dewitt equation to loop quantum gravity is driven largely by some technical intractability of solving the Wheeler-Dewitt equation and chasing these kind of wave functions.
But like we get out like what Klaus was also describing, like an effective time-dependent Schrödinger equation, right? And without filling in the details, you can see from a principled way, you can get out also the usual probabilities associated with that type of equation.
A bit out of time, the last question from this.
So you said this quantum correction is going to wash out, the case is going to wash out in the statistics. But we're talking about dangers, right?
Not these quantum. So in the classical limit, this is going to be negligible, the quantum correction. So in the classical limit, you restore general covariance. But quantum corrections are going to be important if you probe the quantum gravity regime, right?
The argument that we made, okay, in the Lorentzian case, flat space-time, these things would wash out in the statistics.
Well, so let me repeat it. So the simplest Bohmian formulation in special relativity employs a preferred space-time splitting, okay, preferred frame. So it violates Lorentz invariance. So you might think, okay, this is going to show up in the experiment.
Right.
But I think it doesn't.
Yeah.
And we understand why it doesn't, because it's washed out in the statistics.
Right,
So.
I mean, the statistics of the number of particles that they're working with, I mean, in quantum mechanics.
No, just by the Born rule, because of the Born rule.
Sorry?
Because of the Born rule. The Born statistics.
Right,
It was,
here we will be dealing with one, I'm trying to understand statistics of what?
okay.
Have a single universe which has one particular realization of your, I mean, I'm dealing here with a case which I have a single realization, not a
Sure, yeah.
ensemble of universes, and it's clear to me that this is...
Yeah, and I have only a single scalar field and a single metric.
Right.
But like the scalar field, well, it's all over space, okay, and you can look at the local values of that scalar field, right? And then this is how you effectively construct an ensemble. Okay, I have my scalar field here, locally here, can associate independent wave functions to that, and then I can look, does my Bohmian statistics match the Born statistics or not, and so on.